Have you ever wondered where truly great scientists find their inspiration? Thanks for joining us for this episode of Lessons from Lab and Life. I'm your host, Lydia Morrison, and I hope that our podcast offers you some new perspective. Today's lesson is in finding and maintaining inspiration. I'm joined by Chris Noren, Scientific Director of the Chemical Biology Division at NEB, and Angela Belcher, Professor of Biological Engineering at the Koch Institute of MIT. Today, we're going to be discussing finding inspiration in perhaps the most unlikely of places.
I am Christopher Noren. I'm the Scientific Director for Chemical Biology at New England Biolabs. And today, I am ecstatic to be joined by the James Mason Crafts Professor of Biological Engineering and Material Science at MIT, Angela Belcher. Angie has spent her career at the interface of molecular biology and material science, specifically the use of filamentous bacteriophage as a template for material deposition. Angie, thanks for joining us today.
Thank you, Chris. It's great to be on this podcast, and it's great to have you in my lab.
The very first time we met in person, you gave me an abalone shell. So the question is, how did abalone shells inspire your research?
Well, I've been interested in how biology makes materials, like hard materials like calcium carbonate and calcium phosphate and iron oxide-based materials, because nature, through a very long evolutionary time period, learned how to make inorganic materials at the nanoscale under ocean conditions and ocean pressures, and didn't use toxic materials. And to me, that was fascinating. I actually did my PhD on how abalones grow shells. They actually use proteins to nucleate and control the crystal structure. They grow the metastable crystal structure, which is the beautiful mother of pearl-like structure, and they grow calcite, which is the thermodynamically most favored structure, and they do that as kind of a quick way of growing calcium carbonate. And they can switch back and forth between it, and it's all controlled by proteins, which means it's controlled, at the genetic level. And so I've always thought that life did a great job of making inorganic materials, hard materials, but could have had more opportunity, could have used more elements and made more kinds of materials just besides the handful of materials they made. And so my goal when I was finishing graduate school and when I was a postdoc was, wow, how do you get biology to make more technologically important materials like semiconductor materials? When I was finishing graduate school and when I was in a postdoc, it was kind of the explosion of nanoscience. So nano, just like it is today, was becoming more and more important because people were realizing to get to the next generation electronic devices, we were going to have to shrink the electronic structures. Well, biology already makes interesting materials at the nanoscale. They just don't make interesting electronic and optical materials at the nanoscale. So my goal was to make materials like an abalone makes calcium carbonate or shell, but have an animal or organism or biology make electronics.
So you told me that first time we met that your approach to recapitulating the construction of complex materials on a biological template is based on glancing through the New England Biolabs catalog. So can you tell us how that inspired the projects going on in your lab?
So I had heard about this idea of phage display. I'd read some papers on it, but I thought there's, being a solid state inorganic chemist, it's going to be really hard to make a library, a phage display library. And about that same time, I was flipping through the NEB catalog, and phage display libraries were available. You could buy them. I didn't have to make one, which would have taken all my time to figure out how to make one. At the time, we were interested in gallium arsenide, and indium gallium arsenide. And I remember we were talking back and forth with tech services, and we're like, okay, well, we have this single crystal gallium arsenide, and it's in a Eppendorf tube. And what we want to do is we want to bind the phage to the single crystal semiconductor and then elute it off. And so we were going back and forth talking to you about how to approach that. So I think we used gallium arsenide, we used iron oxide, and we tried maybe indium phosphide materials at the time.
Tell us about the airplane wings.
So we started working in batteries. That was really our first device application we started working in the lab, because first we started using phage display to discriminate and bind materials, and then we started using phage display to start growing materials. So we started playing around with that. We started making all kinds of materials. Started making column 2, column 6 semiconductor materials like zinc sulfide, cat sulfide, selenide-based materials. We started making metals. We made fuel cells, actually kind of record-breaking fuel cells out of phage. And we started making battery electrode materials because battery electrode materials like lithium-ion batteries, one of the things that is allowing them to get better and your phones to get smaller and such is nanostructuring these materials, because nanostructuring the anode and cathode materials of lithium-ion batteries allows favorable kinetics for energy storage. And so you think about the beautiful phage as being, only 880 nanometers in length and, 10 nanometers or so in diameter. Now you can grow a lot of really small nanoparticles on that structure that are strung together as a linear string. And now you can make, millions or billions of those. And so we started using those for battery electrodes. I think we started working on anode materials first and published a pretty high impact article on that. And then we started making cathode materials and published some high impact articles in cathode materials. But then we started making films and foams out of these, because remember that they're monodispersed. And so we made liquid crystals out of them, we got high impact journal articles out of that. But you can actually make kind of random foams of these materials that go towards aerogels, meaning that they're mostly, but then space. You can put a smaller amount of templated inorganic materials on them. And so then we started making them into shapes. And so now we can make them into shapes like airplane wing shapes. And we started a project where we're trying to double the distance or the time that an unmanned vehicle or a drone can fly based on what we call structural batteries. So in this case, the battery is part of the structure of the drone. And so it's not like you have a drone and then you clip in the battery. In this case, the wing of the drone is the battery. And the wing of the drone is also a virus-based battery. And so that's an area that we're working on. Another thing that we worked on phage were, at one point that relates to airplanes, is that we used phage to find defects in airplane engine blocks as well. And the idea there was that at defects, you're going to have a change in the chemical structure. You'll have more oxide at the surface or more dangling bonds. And so a phage should be able to see the difference between a collection of dangling bonds and a perfect structure, and we showed that as well.
So working at the interfaces, I've spent some time at interfaces myself. Do you find that there's a certain amount of issues with communication? You actually have to evangelize your position at the interface because so many people like to be in the middle of a discipline rather than around the edges like we are.
So I do. So I think that now it is becoming much more acceptable to do that, and I have faced a lot of scrutiny in the past. Every time I try to go into a new field, I find pushback, and I think it's I never say I want to be the world's expert in X. I basically say, is there something in our approach or toolkit that can help solve this problem? And my PhD advisor said to me when I was a graduate student, he wasn't sure I was tough enough to be a professor because I took things pretty personally. My first grant proposal I wrote as a young professor was on using phage display to find a DNA sequence, a coded for a protein sequence for gallium arsenide and indium gallium arsenide and such. And the review came back that I'm insane. And it says, "She is an insane!" exclamation point. That was the only thing on my review, and it was quite crushing.
You showed them.
Yeah, I did show them. But now being, having insane ideas are great, right? But you have to have sane ideas that are somewhat grounded in reality. And I felt completely comfortable that our ideas were grounded in reality because organisms had done it already.
Exactly.
But just not with these materials. Now, gallium arsenide ended up being the wrong material to choose, ultimately, or not the best material to choose, but we went systematically through the periodic table. And I did a report recently, which I think we've made 150, maybe more than 150 materials that are phage-based materials that phage have, well, obviously phage have never genetically coded for these materials before, but biology has never coded for them. And so, I have pushback, but I think that, like any person, you have to, pick yourself up and dust yourself off and move forward. Not everything has been successful, but not everything's going to be successful. I think, keeping your eye on the big picture, what you want to do. A lot of things that students get really excited about, it's the new direction we come into in the lab. It's the students say, oh, I really want to work on this particular topic. We've never worked on it before, and we'll sit down and we'll sketch it out. And we'll say, okay, we can see an avenue of getting there, and then we'll approach it.
Can you tell us about any other, besides abalone shells in the Biolabs catalog, any other blue sky sources of scientific inspiration?
So, to me, I tell my kids this, that, I hope you meet many people that love science as much as me, but you'll probably never meet anyone that loves science more than me, because I just love it. I love everything about it. I love proteins and I love molecules, and I like thinking about how they interact. And it's such a joy to be able to do this for a living. Think about molecules, build structures, solve problems. That it just fills my day. And so we're constantly thinking about what are the most pressing problems on the planet, because my group is focused on what are the most pressing problems on the planet. And so we organize around themes: energy, the environment, healthcare, water, are some of the major topics that my group works on. And so then also, just like you're flipping through journals, we're always doing the same thing to try to understand what are the limitations to solving things around batteries, around solar cells, around water purification, around finding small structures. And we kind of delve in, we jump in and say, well, what are the limits to the current technology? And then the question we ask, well, does biology have a way of getting around that? Because biology obviously is really good at solving problems and getting around issues. Usually it takes millions and millions of years, but using phage display and basically the technologies that we've developed in my lab around growing these kinds of materials, we try to see if we can have a biological solution to that.
Angie has 2 small children, and obviously you're trying to get them interested in science. But how did you become interested in science?
I was very young when I got interested in science, and neither of my parents were scientists. But I had this idea from a young age that I wanted to do something important. And I thought about 2 things. First thing I wanted to be was an inventor, but I didn't have any good ideas. And I grew up in Houston and San Antonio, and it's really hot there. And I'd go in the summers and I'd say, I'm not going to leave the garage until I invent something new. And I'd be in there sweating and everything, and I'd be like 6 or 7 or 8, and I never really came up with any great ideas. But I thought invention is something that is important. And then after that I thought, well, medicine, that's something that's important. So maybe I'll be a doctor. And so I was also lucky as a young teenager to live in Houston near the medical center. And I got to go to, visit the hospitals and hang out in the libraries in the medical schools. And I started studying, what I could figure out about medicine. But what I really realized is I loved molecules. And I got interested in genetics when I was, 13, 14 years old. And I thought, wow, that's so interesting. How do you go from, DNA to a person? And so, I started thinking I was going to be a doctor. But by the time I was in my first and second year in college, I loved molecules so much that I knew I wanted to go in that direction. Now you think you can be a doctor and love molecules, but I think I loved molecules more than the idea of being a doctor. And so then I pursued a study which was design your own major, and I did a major that was chemistry, biology, physics, geology, because I was interested in the origin of life. My first degree is in creative studies, which is basically design your own major. And because I was interested in so many topics, I didn't want to specialize, and I got really interested. And this is so related to phage display, so it was like written on the stars from the time I was a kid. But I was interested in how did we get from the first small molecules to larger replicating molecules, and then cells and humans and everything else. And I remember reading about, it probably happened at interfaces. It probably happened at the interface between, rocks at the ocean shores, and that was, silica-based structures and clays and, maybe carbonates. And so I was thinking, wow, it's the interface between rocks and small molecules and organic molecules that led to life. And now everything I do is the interface between, proteins and rocks, basically.
Well, speaking of interfaces, you just dovetailed very nicely into my next question. All of your science seems to be at unexpected interfaces of disciplines, such as between molecular biology and material science, rather than falling squarely within a single discipline. So what is it about you personally that enables you to think so far outside of the box?
Well, I think that I feel it was my undergraduate degree in creative studies, which basically allowed me to put any fields together that I wanted. And so I feel really, really lucky, and I try to emphasize this with my children as well, is what's important is to find out what you love and then do that. And I've been very fortunate that my whole career I've only studied what I love to do. And then for my PhD, I work between Galen Stuckey, who's a materials chemist, Dan Morris, who's a molecular biologist, biochemist, and Paul Handsome, who was a physicist. And I work between the three of them. And I think that was actually instrumental in learning to think about a problem for multiple disciplines. Because if you think about an abalone doesn't say, I'm going to build a shell like a physicist would, or I'm going to, it takes different disciplines together and works together to build the best shell it can. And that's what I'm interested in doing. I mean, ultimately, I'm an engineer, so I want to solve problems. And I don't really as much care how I get to the problem as long as it, is economic, as long as it's environmentally friendly and things like that. But I just want to solve problems. And so I basically use what's in the toolkit to solve the problems. And then it goes back to, relating to the problems that of the world that I'm interested in. But a lot of it's student driven. And so here I am talking about, we do this. Of course, I'm a professor, so I don't do anything. And so when the first couple of tech calls, that was me. But, since then, my students do, I haven't done an experiment myself in 15 years.
This is a two-part question. The first part is, what advice would you give to a scientist at the beginning of their career? And then as a follow-up, what advice would you give to a scientist at the middle of their career?
So for undergraduate, the advice that I give students when they're trying to decide their major or classes to take are to study what you're very excited about. And so I think that's the most important, is to find something that you're really passionate about. And the other thing I give people at that stage is, even though I didn't follow this myself, is I think it's really good to pick a major and become an expert in it. At the undergraduate level, you can add on double majors, you can add on minors. But people say, what if I do a little bit of this and a little bit of this? I think you should become an expert. Become an expert in chemistry or biology or mechanical engineering. Pick an area to become an expert and then add on to it. The other thing I say is for graduate school, it's the opportunity to make a pivot. And so, okay, now I become an expert in chemistry or biology or any of geology, any of those topics. Add something else on that you think is interesting and become an expert in that. I think instead of picking and choosing a little bit of depth in everything, is what I kind of do now. But I have a very deep underlying knowledge in a couple of fields, and then as you add on, it gets easier to learn. It gets easier to see the connection between those, and so. That's what I say. And then I think postdoc, if you do a postdoc, again, it's this time to really take a kind of an extreme pivot because now you have all this expertise that you've spent years cultivating, and now you can really go outside your comfort zone and add another field to it. And I think times are different than when I went to school, and the world is different and everything. But I really think that if you can, find something, and I tell this to graduate students, graduate schools has ups and downs. You want to have more ups than you have downs. So pick something that you really love and that you're really passionate about, because you have to have that to keep you going, to keep the big idea, because there's going to be days when experiments do not work. It's going to be days when classes are hard and when you get rejected. But if you getting rejected on something you don't love, that makes it really hard. So you're going to have ups and downs, so trying to have more ups than you do downs. And like I said, I feel like the most fortunate person in the world because I get to study what I'm very interested in.
Okay, so what advice would you have for someone in their 40s who's been doing science for 20-some years?
I think that it's, keep adding new things to the mix. And, I'm a really focused person, a really unfocused person at the same time. I've always kept my expertise focused around organic and inorganic interfaces, but I keep adding different fields. Like we added cancer to the mix, 6 or 7 years ago, in my group where I had to learn everything from the beginning. And of course, I have really smart students who and great colleagues who help teach it to me. But I don't get bored because there's always something new to think about. And I'm the kind of person who loves to think and learn all the time. And people say, don't you feel uncomfortable when, you walk in and you're, not the smartest person in the room. You may be the least knowledgeable person in the room. I said, that's a great starting point because all you have to do is go up. You can't go down, right? Exactly. And so, I'd say that to keep adding new fields and learning and thinking about new interfaces. Now, that being said, mid-career is tough just in general because funding gets much tougher in mid-career. And so I'm not trying to make light out of that, but I do think it's important to keep fundamentally grounded in what you're interested in and what your expertise is, but then look around and see what are the new directions that are being funded in science and what is your expertise that you can have that helps pull you in a new direction you're interested in, and it might be a direction that has, new area of funding. And then everything that we've ever done in my group has been a collaboration. And so working with other people that you really like, the collaboration of the graduate students, I think working with students keeps you young.
I found that as well.
I like working with freshmen, sophomores too, because they still think anything's possible. They're in that upswing.
They're so dewy-eyed. It's like you can. I have all these mini preps. Oh, I'll do them.
Yeah, because it's super fun, right?
Exactly.
But then I think working with students keeps you young, keeps you motivated, and it keeps you on the edge of technology because the grad students that I get coming in today, what they had as an undergraduate in their biology classes is completely different than what we had in our biology classes. Exactly. And they're always pushing me outside my comfort zone, and so I think that's great.
Okay, well, thank you very much for joining us today, Angie, and thanks for fitting us into your busy schedule. And here's to many more years of working with beautiful M13 bacteriophage and doing interesting and fascinating things with it.
Well, thank you so much for having me and for coming to visit my lab and for helping me prove that my initial idea was not insane.
If you enjoyed today's episode, please tune in for our next episode in which NEB scientist Becky Kucera will examine the lessons she has learned from Carrie Mullis and the advent of PCR.